Ladies and gentlemen, hello and welcome. Coming to you once again, not quite live from One Take Studios, where we are looking at graphs of other trig functions today. What does that mean for other trig functions? Well, I'm assuming that you have some knowledge right now of sine and cosine graphs. So if you don't know anything about sine and cosine, I'm probably going to lose you pretty quickly. The goal is for me not to lose myself because there's a lot of detail here and some really cool stuff. All the graphing we're going to do today is without calculators because who needs a calculator to understand these? You don't, I promise you. Alright, so ladies and gentlemen, y equals cosine of x. Just as a brief recap, cosine is a maximum of 1, a minimum of -1, and cosine always starts at the highest point, and what I'm doing is what I call a 5-number summary. If I can get 5 numbers in place, then I can have my cosine curve. So, cosine starts and ends at the highest point. In the middle, halfway through, cosine is at its lowest point, and then in between those, right smack dab in the middle. It's kind of like slicing up a sandwich. I just split it into 1, 2, 3, 4 pieces. Kind of like if you think of the unit circle, there are 4 quadrants, 1 piece for each quadrant. So here's piece number 1 going from 1 down to 0. This should create a lovely wave type of shape. Quadrant 2 going from 0 down to -1. Quadrant 3 from -1 back up to 0, and quadrant 4 from 0 back up to 1. This would then, of course, keep going and continue making lovely, lovely waves. Please, if you are graphing this, don't graph the ends off in space. This is not a parabola. 1 is the highest that it gets, unless you've done something to mess with the equation. But right now we are looking at base models. Alright, now speaking of base models, I'm going to actually go ahead and extend this a little bit farther this way and a little bit farther this way because of what we are about to do. I said graphs of other trig functions, so why do I care about cosine? Do you happen to remember what cosine's reciprocal is? Yes? No? Maybe? Alright, so we are talking y equals cosine's reciprocal is secant. Secant of x. Alright, I can use cosine to help me graph secant. And if I do that, I can actually assemble this graph pretty quick-like. When I say that these are reciprocals, I mean literally that they are reciprocals. Rawr, you flip things over. So what happens if I have a cosine value of 0? What is the reciprocal of 0? Undefined. Ladies and gentlemen, cosine is nice and flowy and yay, happiness and joy, but secant is not as flowy. At 0, there is no reciprocal, therefore there is no value. So secant actually has asymptotes in the graph. Wherever cosine would have been 0, all of a sudden what we have is an asymptote instead. And so that would keep going. Every time cosine hits 0, we would have an asymptote for secant. What does it look like otherwise? Well, these values flipped over actually end up kind of flipping the curve as well. So what it looks like when you start graphing these is that coming up to meet this lowest point of -1, we would have essentially like a parabola looking thing that then curves and backs down the other direction. As these values get closer to 0, these values get farther away. That's kind of it. What you see in red, that is part of the graph of secant. On this one, same thing. We're coming down to meet the highest point. Once we hit it, we hit that point right there and go back up. And ladies and gentlemen, that is part of my graph of secant. So what secant kind of looks like is a series of parabolas. But are they parabolas? No, they are not. Not technically. All right, so this is going to keep going. These are asymptotes, so these graphs get very, very close to the dotted lines, but they do not cross them. And that's it. That's how I graph secant. I draw myself a quick sketch of cosine, throw in asymptotes wherever it equals 0, and then just bounce. Bounce off the hills, bounce off the valleys, and keep going. So everything that you see in red is the graph of secant. Everything that you see in purple is the graph of cosine. Alright, so not super crazy. Again, if you notice, we are repeating this every 2 pi, because if you go around the unit circle, since cosine repeats itself every circle, every 2 pi, secant also repeats itself every 2 pi. Alright, so this thing has a period of 2 pi. It is a periodic graph. It repeats every 2 pi. Again, unless you've done something to mess with it. We'll mess with it here in a second, I promise. Alright, so what does that mean about cosecant? Well, sine, alright, so sine is going to be similar. I'm going to do a 5-number summary, just like I did for cosine. I've got my highest point is 1, my lowest point is -1. Sine always starts in the middle, ends in the middle, as in the middle. So there's 3 of my 5 points for my 5-number summary. Halfway between 0 and pi, we are at the highest point of 1. Halfway between pi and 2 pi, we're at the lowest point of -1. That's my 5-number summary and sketch. Drawing one hill, drawing one valley, and again, at 2 pi, it repeats itself. That's first quadrant, second quadrant, third, fourth, going around the unit circle. Those are the values. So we've got thetas on the x-axis and the trig values then on the y-axis. This would, of course, continue going, next hill, next valley, so on and so forth, next valley, next hill, both directions. Again, constant wave, 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 wave. What does that mean for cosecant? So if I'm graphing y equals the cosecant of x, again, if I'm graphing cosecant, I sketch sine in place first, and I use that to create my drawing because it makes my life easier. Again, they are literally reciprocals. Flip, so anything that is 0 here does not have a reciprocal. So asymptotes galore, there's an asymptote there, there's an asymptote there. There's actually an asymptote on the y-axis as well. It's a little bit hard to see with my drawing probably, but there we go. And again, the graph is going to look a heck of a lot like secant. Bounce off the hills, hit right at the top, turn around, go back up again, stay between the asymptotes, and you bounce off the valleys. Hit that point right there, and then just that one point only, turn around, drop back the other direction. Ladies and gentlemen, that's it. And then there would be another hill coming up, there'd be another valley, and again, it would just keep repeating over and over again. That's it. So I think those aren't too bad. Life, of course, does get interesting from time to time. And so speaking of interesting, yeah, I just have one thing on this page. Okay, here we go. So what I wrote is this right here as a reminder. Y equals a times the sine of b times x minus h plus k. What are these things? These are all things that we have seen previously in the year. These are all transformations. A is our vertical stretch of compression, also controls reflections. B is our horizontal stretch of compression. H is my left-right movement. K is my up-down movement for translations for H and K. So what I'd like to do is try to put several of these into play at one time and see if we can make this make sense. So even though I wrote sine there, this actually works for all trig functions, and right now we're going to try to make it work for cosecant. Alright, so that means we're going to look something like this when we're done. Alright, so putting this together, again, looking for essentially a sketch of sorts, I'm going to do this. I'm going to draw, that's what I want to draw, right? Yeah, maybe I'll go one more. I got lots of space here. And here's going to be my x-axis. Draw that out a ways. Okay, things that I know. This right here is my amplitude. It has an amplitude of 2. What does that mean? Instead of going up to a high of 1 and down to a low of -1, this is going to go up to a high of 2 and down to a low of -2. Except that this guy also plays with this guy right here. Notice this -1 is not in parentheses. Therefore, it is not h. This is k. And what does k do? It controls downward movement. So what this thing is doing is we are saying that, actually I should have drawn farther. I'm going to extend this as well. And there we go. That makes me happy. All right. So everything is going down 1. So instead of everything being centered on the y-axis like it was last time, everything is now centered at -1 instead. This dotted line is not an asymptote. I just like to have a visual of my new center line so I know where everything is going to be placed around my graph. So if this is my new center line because everything went down 1, I am going up 2 and down 2 from here. So if I am at -1, going up 2 puts me at 1. So 1 is actually going to be my highest point, but then from here, from my center line, I'm also going to go down 1, down 2, and this right here, ladies and gentlemen, -3, that's my lowest point. So this is a combination of merging my amplitude with my fact that everything's been translated down by 1 unit. So we're going to go up 2 from the center line, we're going to go down 2 from the center line, but the center line moved. Alright, so high of 1, low of -3. What else do we know? Well, let's see, 1/2 is B. Okay, so this was a vertical stretch. We pulled it taller, stretched it out. This, what is this? Alright, so 1/2 is vertical stretch or compression. What do you think? If you remember, anytime we affect the x, strange and unusual things happen. And so actually, even though this is 1/2, this is going to be a horizontal stretch as well. A little formula, hopefully you've seen before, is that period equals 2 pi over b. Period equals 2 pi over b applies for sine, cosine, secant, and cosecant. So if typically this has a period of 2 pi, so normally it would take us 2 pi to complete one cycle before we restarted ourselves again. This is b. This is 1/2 right here, all right? And so if this is 1/2, what happens if I do 2 pi over 1/2? Well, 2 pi over 1/2, how do I divide by a half? Multiply by 2. What actually just happened? This thing got stretched out. So we are not trying to wrap everything up and restart by 2 pi. we are going to stretch it way out to 4 pi. So I'm going to label this way down over here as 4 pi. Am I drawing this to scale? No, I am not. I don't. I sketch these things and I label. If you have them well labeled, probably have a teacher who's going to be okay. Graphing these in the calculator, quite frankly, you lose a lot of what's actually happening, which makes me sad. All right, so if I think about cosecant being the reciprocal of sine, and I think about sine's graph, sine starts in the middle, ends in the middle, and halfway through, so here 2 pi, because 2 pi is half of 4 pi, would also be in the middle. So part of my sine graph would go here and here and here. And then, well, let's see. We are talking halfway between the beginning and middle is the highest point, and that's going to be, we said, at a height of 1, which half of this is going to be 1 pi. Again, we're stretching it all out. And then this is going to have to be 3 pi right here, and that's going to give us our lowest point of -3. So what I'm drawing right now is sine, knowing that if I can get sine in place, cosecant is not that far to follow. So up, hit the highest point, back down to the middle, not the best graph I've ever done, and down to the lowest point, and back up to the middle, and again that would keep going and would repeat after that and would continue. That is not the graph of cosecant, that is the graph of sine. What does it take to get cosecant? Not much. Again, all right, so everywhere this was 0, so to speak, which is the center, but because it was moved down, this is actually still going to be an asymptote. So that's an asymptote, that's an asymptote, this is still an asymptote. Turn it around, go back up. There's one. Turn it around, go back down. There's another. That is my graph for cosecant. It works essentially the same way. If I can get sine in place, I can graph cosecant. Ta-da! Yes, I realize that these are not zeros, but because of that -1, everything got moved down. Same thing. All right, so you got this. You can do this. So now we can do sine and cosine and secant and cosecant. What does that leave us with? Oh, yeah. Yeah. So, tangent, tangent, tangent. Okay. Question mark right here. Ladies and gentlemen, if you have a unit circle, please take a look at it. If we are going to graph tangent, y equals tangent of x, look at the unit circle. Where is tangent undefined? All right, tangent behaves differently than the other 4 that we've talked about so far. Where is tangent undefined? Well, all right, so if we're thinking about this, actually I'm going to hold off on that. Tangent does not have a value at pi over 2. It is undefined at pi over 2. That's going to be an asymptote for tangent. Also, if we go backwards, this is half a pi in the other direction. We're talking down through the, basically to the bottom. Through the 4th quadrant, we've got another asymptote here. So essentially, asymptote, asymptote. Quite frankly, there's also one at 3 pi over 2, is there not? Because 3 pi over 2 and -pi over 2, those are coterminal. This also doesn't have a value. Notice the distance between -½ pi and +½ pi, between ½ pi and 1½ pi. The distance between asymptotes is 1 pi. We don't have to go around the entire circle. We don't have to find 2 pi before we start over again, like we did for sine and cosine. If you look at the unit circle, the tangent values actually repeat every 1 pi. And just like we did on the last one, where we said, hey, this is going to be 2 pi over b to find the period to see how long it repeats, this would be pi over b instead of 2 pi, because the original repeats every pi. These I really do sketch. I don't pull a lot into this. In my mind, if you know where the asymptotes go, you are really strong. If you know where the center is, because what's the tangent of 0? 0. Tangent in the 1st quadrant is positive. Tangent, if we go down a quadrant in the 4th quadrant, is negative. That's what tangent looks like. If you actually graph the values from the unit circle, that's it. It's a swish. Pi over 2. No, sorry, pi. Pi, tangent is 0. If that's 1st quadrant, this is 2nd quadrant. Tangent is negative in the 2nd and positive in the 3rd. That's that same repeating pattern over. So every pi, it'll repeat itself. That's it. Can I do stretches and compressions and all that kind of fun stuff? Yes. Usually I don't pay, again, because I'm doing largely sketches, I don't pay a lot of attention to stretches as far as vertical and horizontal, vertical is concerned. I do pay attention to the horizontal ones. And so let's take a look at cotangent and then see what that might look like if we mess with it a little bit. All right, so let's think. What is the difference between tangent and cotangent? Again, they are reciprocals of each other, right? So look at your unit circle. Where is cotangent undefined? Well, because it's a reciprocal. Every place that tangent was 0, cotangent is undefined. So tangent has 0 at the origin. That means that, again, my y-axis is actually going to be an asymptote. Really hard to see, but true, that's an asymptote. And if we look at this one, pi over 2, that was an asymptote. It's no longer, but pi was a 0. Zeros become asymptotes. And other direction, negative half pi was an asymptote for tangent, is not for cotangent, but at negative pi, this would be an asymptote. So they are offset from each other. Tangent splits itself in half across the origin. The origin actually is on an asymptote for cotangent. The shapes are similar. What was an asymptote at pi over 2 is a 0 for cotangent, and what was an asymptote at negative pi over 2 for tangent is a 0 for cotangent. These are reciprocals. But this is still essentially the first quadrant. All right, we're coming right up from 0, and everything in the first quadrant is positive. So it's like this, but in reversed. First quadrant positive, swish. Second quadrant negative. And there we go. Same thing. Same image, but again, just sort of inverted. This would be my fourth quadrant, this is my third quadrant, and again, third quadrant cotangent is positive, and fourth quadrant is negative. So visually, what's the difference? Tangent starts lower left, swings up. Cotangent starts upper left, swings down. Here, the period is split in half across the origin, half the period on one side, half the period on the other side. Here, the origin is an asymptote, and all of the period is on one side or the other. You can still see this is a total distance of pi and a total distance of pi. So this has the same period, tangent and cotangent. Every pi is going to repeat itself. All right, last thing for the day. Let's see if you can put this together. All right. What is this? Well, keeping in mind what we've got going on and the things that we said before, do you remember what this does? This guy is going to be a vertical stretch, which I'm not going to pay a ton of attention to because I'm sketching. However, the fact that it's negative, this means something to me. All right, that right there indicates I'm going to do a reflection. And specifically, I'm going to reflect it across the x-axis. So I'm going to think about that, come back to it for a second. Where do my asymptotes go? If I can figure that out, that's the 9/10 of the battle right there. 2 pi. This is a vertical stretch or compression. Again, because we're affecting the x. Did I say vertical? I meant horizontal. This is a horizontal stretch or compression. Well, even though it's 2, it's like doing pi over 2, so we're cutting it in half. This thing's going to have a period of half a pi, pi over 2, instead of having a period of pi. So instead of going from 0 to pi for a single swish, I'm going from 0 to half a pi for a single swish. That's it. That's all I got for space. That's going to be one swish right there. What happens if I were to keep going all the way to pi? I would have to fit 2 swishes in there because my period is half a pi. Every half a pi it's going to repeat. So again, because it is cotangent, I know that the y-axis is an asymptote. And because I'm finished up by half pi this time instead of 1 pi, that's an asymptote. And this would also be an asymptote. So the difference is because this was 2, I'm squishing 2 in the space where I had 1 before. Now normally, for cotangent, I would start upper left and swing down to lower right. Upper left, lower right. But because I'm inverted, oh goodness gracious, I'm actually reversed. So at this point, that is halfway between pi and half a pi. So in other words, at a quarter pi, that's my 0. And because I'm reflected, I'm actually going to go lower left. You can see where these graphs might get confusing with each other and swing to the upper right. Because this is a horizontal compression, The period is half of what it was, because that's a 2. So we're putting together two swishes in a place where we would have had one swish before. That's what the graph would look like. All right, this, honest to goodness, is probably going to leave you feeling a little bit unshaky and uncertain and uncomfortable. Good. That just means that you're not perfect yet. That's okay. So play with this, piece it together, and yeah, who needs the calculator? You're faster than that. Have fun.